Hi guys, we're back. All right, now today we have this warm up. So let's go ahead, and I went ahead and drew the graph for you, but I wanted to force us into a dy situation. So, oh, I'm sorry about that. Okay, so let's go ahead and take this problem, and you can, again, of course, find it in Schoology under this week's folder. And let's take a minute and pause the video and go ahead. Oh my, I need to fix that. So pause the video and then go ahead and try this problem. And you will need to use dy. All right, I'm gonna let you guys pause there. I'm gonna fix my pen and all that good stuff. And we will talk about it in a second. Okay, yeah. So here we are. Here's my little dy rectangle, right? So the top of my rectangle is this function over here, which is my sideways quadratic. So that's my y times 2 minus y. Whoops, right, square. And then this line is just negative y. So I need to integrate. Let's see, this point looks like it's 0, 0. Where is this one? Y times 2 minus y equals negative y. Like we said, y equals 0. What's that one? So 2 minus y, I don't know why I can't write that today, equals negative 1. Equals negative 1. Let's see, if we subtract 2 from both sides, we get negative y equals negative 3. So multiplying by negative 1, we get y equals 3 here at something, comma 3. Of course, we can figure it out because it's negative y, so it's just negative 3, comma 3. So that gives us our limits of integration from 0 to 3. Our right one is that y times the 2 minus y minus our left one of negative y dy. This is a case where distribution is definitely our friend before we integrate. So 0 to 3, 2y minus y squared minus becomes plus. Go ahead and finish combining before we integrate. Then we get 3y minus y squared dy. I just left my y squared afterwards so that I was hopefully less likely to lose a negative as I integrate into 3y squared over 2 minus y cubed over 3. Evaluated from 0 to 3. So we plug in, that's 3 times 3 squared over 2 minus 3 cubed over 3. And then we love polynomials because that's 0 over 2 minus 0 cubed over 3, which all becomes 0, leaving us with, what is this? 927 over 2 minus, that 3 will cancel one of those 3, so 3 squared, which is 9, which is 18 over 2, which leaves us with 9 over 2. So that's our final answer there. Let me know if you have questions. Mostly I wanted us to practice moving along y and setting up our dy's and thinking about that sort of type of problem. All right, so moving along, let's talk about now, today we're talking about volume. So yesterday we talked about area and how area under the curve, we're taking like these little tiny rectangles, and then the integral is that accumulation of our area to get our total area. And it's really accumulation of whatever we're integrating. It's just that we happen to be integrating an area thing. So the way we get to volume, and this can come about in all sorts of ways. There's lots of applications in real life of where we want to find volume of things that have sort of a spinning type of thing. So any sort of like washers and bolts and other round sorts of things often have these applications. So maybe we're building a spaceship, many different ways we'd want to have a rounded thing. So the idea is we imagine that little dx rectangle, right? And we're going to spin it in a circle. Now, if I take a little rectangle and I rotate it around the axis this way, if you were to look at it, you would see that it would create like a little disc. And the radius of that disk is the same as the height of our little dx or dy rectangle. So this little rectangle right here, this height is equal to this radius after we spin it. So if we imagine that. So that's sort of this first big leap of faith or logic leap here is if I take my little dx rectangle and I were to rotate that around the axis, it would give me like these little tiny disks. Whoops. These little tiny disks. So these little tiny disks are great because these little tiny disks have a very tiny volume. They have a tiny volume because they have a tiny thickness. The thickness is the same as the width of that rectangle. So that's our dx or our dy, whatever we're dealing with. The volume, remember volume is just area of the base times the height or the thickness, which is our dx. So what it is the area of a circle, because we have our little disks, disk or a circle. You guys know the area of a circle. Area of a circle is just pi r squared. It's just r is weird here because r is the height of our rectangle. Okay. Now, this is called disk and washer, and this is technically disk. A washer is really not much different. Washer really just uses yesterday's idea of, say we have this with a hole in the middle, right? And I want to find this area out here. I have to do my big area minus my small area. The way this shows up in a graph is we have our arbitrary function f of x, and say we have this other function g of x, intersect there at 0, and then here we'll call this c. And I want to say rotate it around this x-axis. So you can see this part will be filled in, but this middle part is going to be open. So it's going to be like the idea of the big volume minus the small volume. This is honestly where people make mistakes, because what happens is they have this situation where they have a circle with a chunk taken out. And this little one we call baby R, and this big one we call capital R, because we're mathematicians and we have no imagination, and big R means it's big and little r means it's little. Sometimes we call them R1 and R2. But the idea is we're looking for this outer ring area. And I have to do that by doing my big area, as in pi times big R squared, minus my small area, which is pi times little r squared. Now what happens, the mistake that people make is they try to subtract the r's from each other. R minus r squared is not the same as r squared minus little r squared. So you can't just like do this first and then square the whole thing. That totally changes things, and so that's what backs people up, because that's basically what we were doing right with our area, is we were doing our differences there and then doing that. We have to find our area before we integrate into volume. So we're going to set this up as like I was saying, they're little disks. So it's going to be an integral from, like in this case, 0 to c. Now our big radius would be from our axis of rotation to f of x, so our axis of rotation, to whatever our f of x is. So in this case, it's just f of x, right? So that's the distance there. But to get our volume, we have to go pi r, but r in this case is f of x squared. And that would be my big volume, right? And then I could subtract from that this open volume. And so this open volume, 0 to c pi g of x squared. Now this is what I was talking about with up here with the mistake that people make. Is it's okay, we have same limits, right? 0 to c. Most of the time we move pi out because it's a constant. But we have to do f of x squared minus g of x squared. That's the part we have to be careful with because it's big R squared minus little r squared dx. So, right, the pi r squared gives you your area, and this dx is multiplied by both of them. So just be careful that we square and then subtract. So let's look at some examples. Let me know if you guys have questions, and shoot me a remind, things like that. The codes for remind are all in Schoology. Let me know if you have any problems. Okay. So our first example says find the volume of the solid formed by revolving the region bounded by the graph of y equals f of x, of the graph of f of x equals square root of sine x, and the x-axis from 0 is less than x to pi, and we're going to revolve it about the x-axis, okay? So you're going to pause the video. You can sketch a graph. Now, when I say sketch a graph, I don't mean you have to do it like from your head. It's totally fine to use something like Desmos.com or your other favorite graphing tool like your calculator, etc., to help you graph. Don't think you have to do that all on your own. Draw a really good picture. Show the axis of rotation, show your dx that you're rotating, and then let's write our volume. And remember, we're dealing with volume since we're taking this little rectangle and rotating it around. We're creating these little tiny, basically cylinders that we are, because they're like little tiny discs, right? Little tiny circles with a small thickness, little tiny cylinders. And then solve the integral. So pause the video, take a minute, try this, we'll come back. Okay, so here it is. I did use my lovely Desmos to graph this. And I see that I want to rotate it about the x-axis. So the first thing I want to think about is, do I have any gap between my axis of rotation and my graph? And so the answer here is there's no gap, so we don't have to worry about that subtracting off, right? So if I take my little rectangle and I imagine spinning it around in a circle, then imagine spinning around the x-axis, I'm going to get little tiny disc circles. So I need to set up my limits of integration from 0 to pi. Now each one of these little things that I rotate, here's my r, is going to be pi r squared, and r is square root of sine x squared dx. And now it just works like normal. So this is what I was saying, we usually move the pi out, 0 to pi, square root squared just gives me the integral of sine x, which is actually a very simple integral. Pi stays out in front, integral of sine is negative cosine, evaluated from 0 to pi. Negative cosine of pi minus cosine of 0. Thinking about cosine of pi minus negative cosine of 0. Don't lose that negative. Thinking about cosine of pi is negative 1. So we get pi times negative 1 minus becomes plus. Cosine of 0 is also 1. So we get 5. Yeah. All right. Let me know if you have questions on that. Really, it should be the big one is 0 to pi of my area x dx, because this is my area. Well, we can call A to B in this one. 0 to pi of pi r squared. And then that's my radius. Okay, let's try the next one. So example 2. We're going to find the volume of our solid formed by revolving this region. And this time, we are spinning it around this line y equals 1. So that is my, that's my axis of rotation. Okay, so let's pause the video, sketch your graph, show where you're rotating. Decide if you want to use, do you want to use dx or do you want to use dy? What's going to be more convenient? And then go ahead. Okay, so here we are. So this g of x equals 1 is also in the same place, right? That's just another y equals 1. So we're rotating it around here. So even though we moved ourselves off of the x-axis, we don't have a hole because this is the center. Everybody follow that? So my little rectangle isn't just f of x, because f of x goes all the way down to the axis here, right? But it's really just the height difference between f of x and g of x. So my radius in this case is f of x minus g of x. And like I was saying, this is where it starts to get intense. What is my radius? And what part do I need to square? So same thing. Let's see. These intersect, it looks like when y is 1. Oh, which is probably when x is also -1 and 1 based on the graph, right? Okay, so I'm integrating from -1 to 1 of my area times my dx, area of a little disk. Area of the disk. Okay, and the area of those little disks that I'm creating, -1 to 1, pi times my radius, which was 2 minus x squared minus 1 squared. So it's -1 to 1 of pi r squared. Right? Then from there, it's just a matter of you guys know what to do. That part isn't the new part. So let's see, we get 1 minus x squared. So this 2 minus x was my f of x. And then I subtracted this 1, which was my g of x. And that's because that's my r here. So hopefully that makes sense. And then you guys feel good with finishing this out. I'm going to switch out of red. For some reason, I don't like doing problems in red. At this point, I would integrate x minus x cubed over 3, evaluated from -1 to 1. Then it should just be an easy peasy plug-in. 1 minus 1 cubed over 3 minus -1 minus -1 cubed over 3. Oh, negatives everywhere. 1 minus 1/3. This makes these plus. Oh, I shouldn't have done that. Let me undo that real quick. So I should actually do it like this. This would be negative, and then this would be positive, right? Then if I make this positive, that'll make this. If I make this positive, that'll make this back to positive, but it'll make this back to negative. We should get plus another 1 minus another 1/3. Let me know if that doesn't make sense. 2 minus 2/3. 6 over 3 minus 2 over 3. We should get 4/3. Somehow I ended up back in red. All right. Hopefully we're doing okay still. Let's look at 3. Okay, so we have this function. So we're going to always start the same way. We're going to start by drawing our graphs, and you can use Desmos if you need to. It's y equals square root of x. Y equals x squared. And then we're going to rotate, whoops, not that. We're going to rotate around the x-axis. So let's pause our video. Let's take a minute, set up the situation, try this problem, then you know what to do. All right, here's our beautiful one. X-axis. X-axis is this axis, so we're rotating it around here. And now we've come across our first one where our little piece that we're rotating doesn't fill all the way to the axis. So we sort of have this situation, I'm going to redraw that. We sort of have this situation of this is what we want, and this part down here is what we have to take out. That's blue. This part down here is what we have to take out. So if we want to end up with this, we can't just like write this distance because we have to base it on where we're rotating from. So we have to base it on, we are going to find this full volume and subtract out this part volume. Just like we were doing yesterday with the areas where we did the big area minus the small area. So that's the really important piece on this, the really important new big thought is that we need to be sure we set up the big volume minus the small volume. Well, the empty volume, I guess, really, the big volume. So our big volume would be to the outside. This would be if it were solid, right? So that would be the integral from 0 to 1 of pi. That radius, let's see, that's this graph, right? That's my square root of x graph. So that would be square root of x squared dx, okay? Then we want to take out this small volume, right? This that's underneath, that's going to be empty. So minus 0 to 1 pi x squared dx. If you set it up like that, you will usually not make mistakes because you did your big volume minus your small volume. And then you can just go straight from here. At this point, I would pull out the pi, x dx, pi, integral 0 to 1, x to the 4th dx. Of course, you could put these integrals back together. It's kind of irrelevant either way. You just want to make sure that you don't mess anything up plugging in. So whatever will make you make the fewest mistakes is the best way to do it for you. So we get 1/2, 1 squared minus 1/2 times 0 squared, which is just a half, right? Minus pi, and then we get 1/5 minus 0 to the 5th over 5, which gives us pi 1/2 minus pi times the 5th, which is pi over 2 minus pi over 5, which we should really probably get a common denominator for by multiplying this one by 5, this one by 2, so that we get 5 pi minus 2 pi over 10, which we can simplify to be 3 pi over 10. Okay. Cool? So same idea and very similar as yesterday, right? So set it up as your big volume minus your small volume, and you really shouldn't make mistakes with your squaring in your order of operations. All right, I believe I have 2 more examples for you. So we have this one, solid formed by y equals x squared, y equals 4. This time we're rotating it around the y-axis. So the fact that we're rotating it around the y-axis is probably a clue that we may need to use dy this time, right? Because we're rotating it this direction. So we need our little rectangles to stick out this way, right? So this is going to be our dy situation. Since we have it in a dy situation, we may need to solve this, okay? So take a minute, let's pause the video. Let's think about this and try it, and then we'll come back. All right, so here's our graph, and let's trace our region. So x squared, and y equals 4. Now I'm wondering if I messed it up, but not really. We're just going to cut it off like this because we're rotating it around here. So even though the graph is symmetrical like this, that part is kind of irrelevant. So we're just going to ignore that because we would only have to rotate it like halfway if we were thinking of it like that. So we're just going to think of rotating this. Here's our little rectangle. So the problem with rotating this is we know we want dy, which means all of our variables need to be y or in terms of y, right? So variables, limits, right, are also y values. So that's fine. This y is 0. And this y we know is 4, right? We don't really care what the x is. That's not relevant to us. And then this is y equals x squared. If we solve it, we get x equals plus or minus square root of y. So You have plus square root of y on this side, minus square root of y on this side. Make sense? So we really just care about this positive one. So we'll just be using this plus root y. So we have the integral from 0 to 4. Here's my axis of rotation, and my rectangle goes all the way down to the axis of rotation, so I don't have to worry about any subtracting off, right? So the height of this rectangle, we're going to make an area after we rotate it, so pi r squared, and the height is square root of y. And then it's easy peasy integral from here. So the question is, do we understand why this pi r squared r is the square root of y? Because r is this height between my axis of rotation and my function. Right, that's my r value. Okay, I'm gonna believe you. You guys know this. So integral from 0 to 4. I'm gonna move my pi out in front of y dy. And this is when I'm like, I love this because this is easy. Half y squared, 0 to 4. So I don't believe that you guys are going to be having trouble, and maybe I'm wrong, and if I'm wrong, please let me know. I don't believe you're having trouble on evaluating most of these integrals. It should really be a setting up thing. So this one, I think we got 8 pi. So let me know if you're having troubles. But really it's just this idea of setting it up, and of course we can move along x or along y. So I think I have one more example for you. I do. And this time we have, it's bounded by x squared plus 1, y equals 0, x equals 0, and we're going around the y. So take a minute, bust out Desmos, whatever you need to. But let's pause this video and let's try this problem. Because if you guys can do this problem, then I feel like you guys have a good handle on things and I think we're doing okay. If you're feeling lost, then that's definitely something we need to address. So we will be meeting all together tomorrow. So if we need to talk about it on Wednesday during class, we can. Okay, so y equals x squared plus 1. That's this graph. And then we are going to rotate this about the y-axis. So we're rotating it about the y-axis. Our little dy wants to stick out this way, right? And it's getting rotated around. And if I imagine like spinning that around, it's creating that little disc I was talking about. We have our dy. This is our r, the height. So what we notice on this is initially our height is like 1, and we're good to go. When we get to here, our height starts to change. So just like yesterday when we set up area with 2 pieces, all we're doing now is we're going to have to set up our integral with 2 pieces, right? So this first one we can integrate from 0 to 1, right? X squared plus 1. Because we're integrating along the y. And this height is always the same. It's just 1 minus 0 pi squared, which is really just the integral from 0 to 1 of pi dy, which is really simple. So don't stress. It really is that simple. And we're going to add to that, and we need to add to that the area, or the volume, that we're going to get from here. Now, the volume we get from here, this is a mess, right? So we need to take this big volume minus this small volume. Now, the big volume would just be the integral from 1 to 2, right? Y equals 2 up here. And then for the big volume, we go all the way from our axis of rotation to the outer edge. So that's going to be that pi minus 0, so 1 squared dy, right? Because we need to integrate along this one the whole time. But then we need to subtract off. I guess I shouldn't have written this earlier. Sorry about that. We need to subtract off this area that would have arisen, or this volume that would have arisen in here, the underneath, right? Because this is open. So we need to subtract that volume away. So minus the integral from 1 to 2 pi. And this one's r is the difference between here and here. But we're moving along dy, and this is not solved for y. So let's fix that. X squared plus 1, y minus 1 equals x squared. X equals plus or minus root y minus 1. We're over here, so we're on the positive square root of y minus 1. So that would be square root of y minus 1. This is 0. We don't really have to put that minus 0 if we don't want to. We, of course, can. It makes our work look beautiful. So here we have 0 to 1 of pi dy plus 1 to 2 of pi dy minus 1 to 2. Square root squared is just going to be minus 1 dy. Now, oh goodness, there's an extra pi up in here. Let's fix that. Now, maybe you're wondering this, maybe you didn't notice this. Either way is okay. I just want to point it out. If you did notice this, yes, we could have set this up as one integral from 0 to 2 of pi dy. Because these are the exact same thing, and then this one's just picking up right where this one picks up, right where this one stops. Like, it's okay to smash them together. Also, if you think about it, we took this whole volume, this big volume here, right, and we subtracted off this little volume here. That would be an okay way to think about the problem too. So if you're wondering, yes is the short answer. Minus pi integral from 1 to 2 y minus 1 dy. Let's go ahead and do this integral. So this is just pi y evaluated from 0 to 2 minus pi y squared over 2 minus y evaluated from 1 to 2. Plugging in pi 2 minus 0, that was easy, minus pi 2 squared over 2 minus 2. I'll use another set of parentheses. Minus 1 squared over 2 minus 1. Hate all these negatives running around. This is 2 pi. Oh, goodness. Let's see. I'm going to leave this. Pi. This is 2 minus... Is that really 2 minus 2? Looks like it to me. Yeah, that's 0. 1/2 minus 1 is negative 1/2. Made it back to a negative. I say this is positive 1/2. I guess I got 2 pi minus pi over 2. Which we know pi over 2. 4 pi over 2 minus pi over 2 is really 3 pi. 2. Okay, so same idea. And really this isn't a big leap from yesterday. The biggest leap is at the very beginning where we turned this idea of taking this little rectangle, rotating it around the axis, and getting a super thin little disc. So let me know if you have questions. Shoot me a remind. Remind codes are in Schoology. So if you need to sign up for that, then please just go to that like updates page. Remind codes are in Schoology. We don't have a ton of homework. I do believe that these have some multiple parts. I think that's what's going on. And then I'll post solutions soon. Hope you have a great night, and I'll see you all on Wednesday on Zoom. Talk to you soon. Bye, guys.